talk about nanofabrication in introduction level is easy, so I don't like to review them. Okay, so here I like to talk about this characterization. Okay, characterization is very important. Okay, so I just give a global view and talk about the microscopy and the surface characterization. Because this is the last lecture, I believe. Okay, so next lecture just review, maybe I'll do some teaching evaluation or something. Okay, the motivation, why it has nanofabrication? Okay, nanofabrication, from nanofabrication we can know the geometry, dimensions, and structure of this atom, molecule, or your sample or something. Okay, so you can know what does it look like. Okay, it's the first reason. Another, you can know the composition or chemical element from the characterization. You know which kind of atom or molecule are compose your structure. Okay. A third motivation is you can know the physical and the chemical property of your sample. Okay, like optical, electrical, magnetic, thermal, mechanical. Okay, from this characterization. So it's a way to see and understand the nano world. So it's quite important. Although my knowledge in this topic is very weak because I have no experience in measure some okay, nanoscale structure, but I just want to deliver some basic knowledge or introduction knowledge to you. Maybe you can learn several of methods. Okay, this is a global picture. You can see this is a global picture for nanofabrication. Okay. From nanofabrication, you can know structure information, optical information, electrical information, and magnetic information. Okay, it has a very different method. So I summarize all the method, use a cartoon picture. I just copy some figure, although I draw some figure by myself. Okay, so in this lecture, I mainly focus on structure information, optical information, on these two parts. Okay, for structure information, we have we use method can know the morphology, crystal structure, and the composition. Okay, I just give you an example how to read this figure. This figure is very easy to read. Okay, for example, scanning electron microscopy we call SEM. So SEM from this picture is a very small picture. Okay, there's an electron strikes the sample, then other electron typically is a valence electron will scan out. Okay, then your equipment just measure this secondary electrons. Okay, this is a SEM. Okay, this is SEM. Okay, so what's the basic way to characterize nanomaterial? Just use electron, photon, ion. Those three types of the particle. Okay, one type particle. You have electron, you have the photon, you have X-ray or ion to strike your sample. Then excite electron or photon or X-ray to detect them. Okay, so let me say again. So basic idea, you use electron or photon or X-ray or ion to strike your sample. Then after that, there's some other electron, photon or X-ray or ion scattered out. Then you detect this scattered out information. Okay, this is the basic way. Okay, SEM is electron, incident, electron scatter. This SEM. Okay. I just give another example, like XRD. It's very famous. X-ray diffraction. Okay, you can see they give an X-ray. Okay, the emit out also X-ray. Okay, know this method we can know the crystal structure used for bright reflection. Okay, because the atom has a periodic structure, I use the X-ray also EM wave. We use EM wave, very high frequency EM wave. We can scatter out, we can know this crystal structure. Okay, you can see this picture. It's XRD. Okay. Another example, I just give another example about this optical part. Okay, for optical part, we have photoluminescence, the very famous PL spectrum. Just use very high frequency light to excite the sample and see this decay rate, see this emission light. Okay, this is PL. Okay, another is called Fourier transform infrared spectrum. You can see this is a photon incident, the photon outside. It's a transmission spectrum or reflection spectrum. Okay, this is called a Fourier transform infrared spectrum. Okay, the incident photon also photon. Okay, similar to another is Raman scattering. Everyone remember Raman scattering, right? Give a high frequency, like a lower frequency, the Raman scattering. Okay, so this is basic I just draw this cartoon picture to you. Okay, give a basic configuration. But in this lecture, I'll talk about SEM, FM, TEM. Okay, for this lecture. Okay, and microscopy in optics. This is a basic picture. Another way to do classification, they give a different classification. One is microscopy, another is surface characterization, and depth profile technique, and non-destructive testing technique. They give another classification. Okay, microscopy. Okay, microscopy, as I said, you just use a photon, electron, ion to strike your sample. Then you detect the scattered particles or scattered particle. Okay, you can use light. Okay, you can use light. Okay, including the dark field microscopy or near field scanning, optical microscopy. Okay, use light. You can use X-ray, use electron, or use ion. Okay, both is okay. Okay, this is many different names. You can see that this is a very rich field. Okay, I cannot understand field very well because this field very rich. Another is called surface characterization. Just detect the surface of a sample. Okay, just detect the surface of a sample. Okay. So this method, for example, if we use TEM, transmission electron microscopy. Okay, I just go to this cartoon picture. You can see what's the transmission. It's TEM. You can see here. Okay, the electron go in, electron out, right? I use electron to strike because the sample is very thin. We can penetrate the electron go out. Okay, we call TEM. So TEM method, typically you can get this volume information or composition. Okay. So surface characterization technique only care about the surface, like atomic force microscopy or scanning tunneling microscopy. I'll talk about this later. All this dashed line, okay, this underline is something I want to talk. Okay. The third type we just know the depth. Okay, know the depth. I think this one is interesting, but I cannot talk. It's called non-destructive testing method. All about method, you just damage your sample. You detect, right? Use electron, ion, or X-ray to strike your sample. You just damage them. Okay. So non-destructive method does not damage them. Typically, you use microwave or use some other technique that does not damage your sample. Maybe radiographic, you do something. Okay, electromagnetics or magnetic static test. Okay, called non-destructive. This is another classification. Okay. So today's lecture, I just talk about this 1, 2, 3, 5, 6. Okay, 6 key techniques. Okay, this is the resolution. It's very important. You can see optical one. All the optical microscopy, film macron. Okay, typically film macron. Okay, then we do the SEM or TEM, become 10 nanometer or 1 nanometer. SEM around 10 nanometer. TEM, SEM is scanning electron microscopy, is 10 nanometer. Okay, transmission electron microscopy is 1 nanometer. This is called scanning transmission electron microscopy. You can see the electron microscopy, the resolution should be like the optical microscopy because of diffraction limit. Okay, this is the main problem for optical microscopy because of diffraction limit. Okay. So let me give a very important content. Okay, in this lecture. Okay, I like to talk about the microscopy first. Okay. Okay. In microscopy, I think because this lecture is nanophotonics, so I just mainly focus on the optical microscopy. Okay. Optical microscopy. So optical microscopy is sit down, please. It's optical microscopy is a very important technique. Okay, I think everyone should know that. So I just introduce a basic concept. One called bright field microscopy. What's the meaning of bright field? Okay, this has a wide field illumination. I means all the samples just was illuminated by the light. Okay. Another, the final collection, including two parts. One is a incident wave from this source. Okay, from this light source. Another is a scatter wave from this sample. Add them together. Finally, okay, this is the basic. They call it wide field illumination. Okay, You can see here, all this is the source, okay? They have incident wave, okay? Go to some condenser and a lens to focus, okay? This is called focus lamp to a sample. A sample scatter, also has some scatter wave, scatter light, go to the lens, and many lens, and go here and do the image, okay? So here, we get two kind of a field. One is incident wave, one is scatter wave, okay? Together, okay? You do not separate them. This is the oldest or simplest microscopy. It's also used current technique. Okay, this is called bright field microscope. Okay, then we see this dark field. Okay, this is very important. What's the meaning of dark field? For dark field microscopy, okay, you can see source is here. Very different in here. It's a condenser. You can see this condenser. I go to the previous one. Previously condenser, you can see they light. They want all the way go to this pinhole. They let all the light go to this large pinhole, okay? But dark field, you can see, they block direct light, right? This block, this is a light stop at this condenser, okay? They stop all the light go directly into object, okay? The direct light go to object stop is important, very important. Only a light from this very small pinhole go around, okay, lens and focus the sample, okay, focus on sample. When it focus on sample, the sample scattering, okay, scattering. You can see the direct light just stopped by this. Only scatter light can go here. So only the green light is scattered, okay, they can go to the lens and collect by this, okay. So this is a very important thing. You can see the direct light, I mean the red color, maybe this and this, they are stopped by this, okay. Only a scatter light can go across this green line, okay. So this is a very, very different technique because only scatter light was recorded, okay. Incident wave from this point are just, block. So you call it the dark field, okay. So for the bright field, for the bright field, we get a total field. We get an incident field plus a scatter field. Okay, so it's a contrast. A contrast, okay, in a sample is caused by the absorption of light. Okay, I mean some light. You can see it's total field. Some field are absorbed by the particle or by this part of sample. Okay, so it's by the absorption. But here, you can see the incident wave. You can see finally the block. This block here. This block here. Only scatter wave. I mean the green line can collect. Okay. So finally this dark field, they get this scatter field. Okay. This scatter field is contrast just come from the light scattered by the sample. It's a very different technique. It's very important in nanoscale called dark field. Okay. The third one is called phase contrast. Okay. Phase contrast. What's the meaning of phase contrast? First thing is it has a phase ring. Only let a ring of light illuminate sample. You can see here. They also block a lot of light. Only has this ring. Okay, the typical is a ring. Okay, go into here. Okay, this is a sample. Okay, this is a sample. You can see it has scatter light. Oh, this is sample. It has scatter light. Okay, go here. You can see here. It's very, very interesting. This is also scatter light. The scatter light is not delayed because it has a phase plate. You can see the green one and the red one. They go to this part. They have some, they have some delay here. But this scatter light just go directly. So this phase plate does not delay the scatter light. Okay, but they delay the direct light. Okay, direct light is delayed. Okay, they can control the light path. You can see this red, it's green. They control this part. Okay. So let the green part and the red part touch this part. This is a phase plate, they can get a phase delay. But the scatter light from sample, no delay. Okay. Then finally, at CTD, they get the incident wave, also get a scatter wave, but not the same phase. Okay, incident wave and scatter wave not same phase. Because the incident wave, they have phase delay here. Okay, that's phase delay here. Okay. But the scatter wave with no phase delay. Okay. So they call it phase contrast. Okay. Let me show you example what's happened. Okay, this is a real work case. You can see the bright field. This is bright. Okay, this is a total field. You can see the dark field. Dark field. This is dark. right? No scattering, right? Because no scatter here, so it's dark. It only has this region, has some white, some scatter here. This is called phase contrast. Okay, you can see there's a different now for these three techniques. Okay, dark field technique is sometimes very useful in nano optics. I show you example. I remember I give this example. Maybe call this part 3 or part 2. I show dark field. No, not this. Part 2. I remember. Yeah, this one. Okay, this is experimental result. This is simulation. You can see this dark field. Okay, this is a particle highly couple each other. Okay, you can see according to dark field. Okay, you can see this. This is very close to each other. It has become a guided wave. Okay, here is well separated. It has interference pattern. Okay, this simulation is that. This is dark field technique. So this is okay, this is three different ways: the bright field, dark field, and the phase contrast. So all the story is that finally collect light is a total field or scatter field or just incident field interference with the scatter field. Or okay, for bright field, okay, finally the collected intensity is a total field. Okay, so the contrast is by the absorption. For dark field, finally collect only scatter field from a sample. Okay, no incident field. Now for phase contrast, they collect incident field and the scatter field simultaneously, but they have a phase difference. They have phase difference. They have interference. Okay, so this is three different ways. Another important called confocal microscopy. Okay, confocal microscopy. This also, I think this equivalent I think is okay, not too expensive to buy the confocal. Okay, but I think for NISOM it's very expensive. Okay, for confocal technique is they add just a spatial pinhole in here. Okay, just eliminate out of focus light. Okay, do you see that the example is a very interesting example? First thing for confocal technique, you use a point source here. Okay, I go to a beam splitter. Okay, beam splitter and go to a sample and focus here. Okay, this is a focus plane. This is a focus plane. Okay, and then this red and a green line. You can see the red and green line is not a focus plane. Okay, you can see that it cannot collect by this pinhole here. So this is there's a well match each other. Okay, so this point go to the beam splitter and focus on this plane, and this reflection of scatter wave from this lens then collected by this confocal aperture. Other red and green light are blocked. You can see, okay, are blocked. So they can focus your sample very well. Okay, they only capture the information from this around here. Okay, okay, but eliminate the scatter wave or something around a different location with this technique. But this technique is quite okay. I think if you do the image, you can buy this equipment. Okay, it's not too expensive, but I think it can overcome some limitation or wide field illumination. So wide field illumination just every point, all the sample just illuminated by the EM wave. But here only a small region. Okay, can collect. You can see this is black. Okay, it goes with pinhole. They're called a confocal technique. Okay. This is a confocal technique. So this is a very good example to focus the light. Okay, but our technique above, okay, they suffer from called diffraction limit. Diffraction limit. If far field measurement is done, I mean if you collect the information from the far field, okay, I mean if the observing plane is very far from this source plane, okay, you lose evanescent wave information. Okay, so they just induce a low resolution or resolution just limited by the wavelengths. Okay, you must use UV light. You use very high light. Okay, to increase the resolution. Okay, so this is the purpose. So I draw this picture many times. Okay, because you can see this part is a propagating wave. This evanescent wave. You lose a blue part. You lose. Okay, in far field detection. Okay, okay. So there's a very famous theorem called a Rayleigh criterion. Okay, Rayleigh criterion. In Rayleigh criterion, the one-point source is a one-point source. Okay, because you only capture this part, propagating part. Then you will do the inverse Fourier transform. You only get this finite pulse. They call it point spectral function. Okay, I taught this many times. Okay, but initially you have this delta source. Okay, so their spectral in k domain is something like this. But here, but in fact, in far field, you only capture this information. So finally, you just get something like this. They call it point spectral function. Point spread function. So what's the diffraction limit? Okay, what is the diffraction limit? You said this 2 point, object 1, object 2. Okay, go to this pinhole. You can see this object 1, this object 2. This is the image. Okay, while the minimum, the first minimum, or diffraction minimum, just overlap, just coincide, or the maximum, or another, okay, or another point. You can see this point, this is the first minimum of this point, so coincide maximum or another point. This is just said, is just resolve. Okay, so use this condition, we can do some calculation. Okay, you can do some calculation. Okay, to get that the angular resolution is just proportional to the wavelength over the diameter of the aperture. Okay, they call it Rayleigh criterion. Okay, everyone should know how to calculate them. Okay. Do you know how to calculate them? Okay. In fact, I give you assignment before. Okay, there's a pinhole. Right? There's some pinhole. Okay, the light sometimes have like this. They have diffraction. Okay. I'll give you an example. This red light. Okay, now this is the blue. Okay, for red light, everyone know that it has they call it it's the delta k, it's the delta x. I can't quite remember. Like some constant. It has called uncertainty principle. It means it has a low frequency if this is delta 2 pi over delta lambda. Okay. If the red color, I believe the angle is larger, the theta is larger. The blue color is theta is smaller. I remember it has a similar to this called the uncertainty principle. Okay. If I draw this correctly. I mean the red, if a red color it can spread more larger angle, if a blue color is a smaller angle. But how to calculate them? It's very simple. How to calculate them? Okay, this is a plane wave, this k, this E. You learn this, right? I give this J, this is J and M, this is equivalent current, okay? And the equivalent current and the magnetic current as this whole, okay? This is the equivalent principle. Then, I put a PEC in here, okay? So J disappeared, okay? J disappeared, just only M, right? Only M. So finally, I get this expression for E field, just 2M. It's just a gradient. Okay, something like this. Delta function, dr prime. You can calculate that. Okay, this is the assignment. Okay. Initially, they had equivalent current J and equivalent electric current and magnetic current. So I put the PEC here. Okay, it only has a equivalent magnetic current because impressed J does not radiate. Okay, so due to imaginary theory, this is imaginary theory. It's a virtual plane. We have 2M in here. Okay, so finally we just get this. Okay, so finally we just get this 2M. It has some constant. This is just a finally expression. I give an assignment to you. This can solve this problem. Okay, so this is all the story. It's free space, very simple. So it's just 2M cross 30G dr prime. G here is just free space going function. So this problem, initially it has equivalent J and M, and equivalent J for the screen. Okay, PEC screen. So then I put a PEC here. It only has M. Okay, only has M here. Okay, because this does not radiate. Okay, so I just draw this better. Not. So this is original program. I hope everyone can understand this. Okay, this is PEC. This is PEC. Okay. This is light. And you can solve. This is K. This is E. Okay. So this program first is equivalent to here. It has the equivalent current J. And this part just J and M. Okay. And this part only has J. Okay, this is PEC, only has J. So this is equivalent current. Then I put the PEC. Okay, I put the PEC here. This is the impressed current. Because J does not radiate, only has M. Then I use imaging theory again. It become a 2M here. In the PEC to the virtual surface. So I use green function, just E equal 2M dot delta cross G. Or something like this. Huygens principle. Okay. So you can solve this problem. You can solve this problem. When you solve this problem, solve this the circle. It has a screen. It has circle to solve this problem. When you solve this problem, you found it's an interesting phenomenon. Okay. So I just use wiki. It's better. We call it area plane. Google, they call it area plane. You can see what happened. If you solve this, area disk. So, type disk. Okay, this area disk. You can see here. When you solve this equation in far field, you will find it has hot spot here. This is the radius. This is the radius. Just first the radius is just a diffraction, 1.22. Okay. When you use the green function to solve that, you can find this pattern. Okay. So this is a very simple. Just do the integral. Okay. Just use this equation to the integral. So M is here, very simple. M just minus 2 over E is a plane wave. You can solve this. So it's not difficult. Then you can solve this many imaging program. Okay, use this way to understand why they get something like this. Why they get something like this. Okay, they also for diffraction. So this is a really criterion. Okay, so you cannot resolve the 2 points even they are very close to each other. Okay, this is a problem for the far field image. Okay, even use confocal, use dark field, you cannot solve this problem. You cannot solve. Okay, if you are very far from. Okay. This is basic. So I think the method to solve this problem is the near field scanning optical microscopy called NISON. Okay. or SNOM, someone call it SNOM. Okay, so this equipment is very expensive, maybe 2 million. NSOM is very expensive. Okay. I'm not sure that our department which group has NSOM. Okay, but it's your group have NSOM?
SNOM.
You have SNOM?
Yeah.
Okay. Is good? Resolution?
I spent nearly 1 year to set up all the.
Yeah. So it's very complicated. Okay. So you can see here the tip they produce ionism wave. Okay. They draw this picture. Okay. Here is very high intensity and there is a low intensity because the field will decay. So the near field it should be around here. Okay. Just 10 nanometer. It should be very close tip for 10 nanometer. Okay. This is a tip. You can see they have the cold part, cladding part, and metal. A metal, the out-coating metal, I believe, first thing is to make this tip unpenetrable. And now maybe it has a plasma effect here. And a very strong near field around its tip. Okay, around its tip. If they couple it to some particle, I believe they have some surface plasma around it, local plasma around it. This is my understanding. So this is it's a real world picture. You can see. This is similar canteen level, similar to tip. There's some ensemble tip. They use a very near field measurement. In some setup, they have two types called aperture and apertureless. Okay, typically aperture ensemble is easier. The apertureless. Okay, they have a different mode. Like this mode, they can use incident wave also collect with a beam splitter. Okay, called illumination collect mode. Okay, or maybe they can use reflection. Okay, this reflection wave, and they collect by the tube, or it's called reflection collect mode. Okay. There are many different collect modes. Can I tell you your group use which kind of mode your experiment? You know?
I'm not.
You don't know. Okay, don't know the detail. Okay. Okay. Maybe analysis mode for okay a different mode. Because this is transmission, collection. Okay, this is transmission. This light and transmission of the sample they collect. Okay, or transmission illumination. Okay. A different mode in aperture ensemble. But I think the main interesting part is this working principle. Okay, very complicated, not easy. Okay, so you can see this diagram. But let me introduce it first. Okay, here is excitation source. Okay, this source from the fiber. Okay, this is a tip. Okay, here, and then tip to excite very strong ionization wave. Okay, interact with the sample. Okay, sample in here. This is the part. This part is important. But one important thing is how to control the distance between the tip and the sample. Because sample is a rough surface typically, right? It's a very rough surface. When you move the tip, if no feedback, you just break. The tip is very impassive, break of tip. So you must have feedback. The feedback is, I think, is a key part. It's a key technique. Here, you can see. They use a laser. The laser goes to a lens and shine. You can see they use laser to shine the tip. Okay, shine is cantilever. Okay, this is a photo detector. It's a photo detector. Because there's a force, you know, I'll talk about it later, atomic force microscopy. Because the tip and atom has a force when they are very close to each other. It's a force called a van der Waals force. Okay. That means when the two molecules or two atoms, they are very, very close to each other, they have a force. This is a force called van der Waals force. Okay. Everyone to hear its name, maybe in high school or maybe in primary school, they call it Van der Waals. Okay, the van der Waals force. Okay, van der Waals force, because it has a van der Waals force, this force will oscillate, you know, oscillate the tip. Okay, oscillate this tip. This oscillation will sensed by the photodetector. Because when oscillate the tip will oscillate, the light, you know, go into the photodetector will change. It will change. You can oscillate, you can see here. Okay. They use, and they get it photodetector. No, oh, this change. And it goes to some feedback system. The control is a piezoelectrical element. This piezoelectrical element can control, you can see the piezoelectrical element. Because I said, there's a force, atom and tip, they oscillate. The oscillator will sense by the photodiode, they have a feedback goes with the piezoelectrical element. This element can be pressed, okay? This is called a piezoelectrical effect. If you add a voltage, they can compress or expand, okay? People expand. They expand here, they just change they can tune this height, okay? Tune this height. Okay. This is a feedback technique. They also use XY scanner, okay? So let me say again, it's very important. Because they have the force, okay? Between the tip and the atom, they have the force. The force is called van der Waals force. Okay, this force causes the tip will oscillate. Okay. This oscillation was sensed by the photodiode. Okay. Then this photodiode, according to this feedback control, to control this piezoelectric to tune its height. Okay. This is a basic feedback mechanism. So this is a this part why is it expensive? Because if you do the small system, you must add AFM, atomic force microscope. This is just AFM part. So this is the reason why it's expensive. If I buy a AFM, just this part, but you from inside they have another part. Okay. So this is very expensive. This part is AFM, very similar to AFM. AFM use this very big feedback technique. Okay. So this is important. Another important thing, how to understand some small result. Okay, this is truncated line defect in photonic crystal. You can see here. This is photonic crystal. Okay, this is a defect line. Okay, similar to waveguide. I truncated here. So I use wave excite. Okay, I get this the C and D. This is N-sum result. Okay, the first is the tomography result because you know the height, right? When you tune, because the different height, they give a different signal. So I know the height of this sample. Okay, because I said they have variable force. The variable force they give a different oscillation. So I know this oscillation amplitude or phase. Maybe we can know the height. Okay, what's the distance between the tip and the height? So I can draw this topography figure. Okay, the C and D just N-sum figure. N-sum figure. It's a scalar wave. Because it's scalar wave, also can go to the fiber. Okay, we can detect or maybe go to another part. Okay. So this is a picture. This is very important. What's the physical origin of this hotspot? What's the physical origin of hotspot? What's your opinion? Okay. Relevant. This is a photonic crystal. Okay, it's a line defect. I truncate that. But I form this. What's the physical origin? It's very important. Everyone can. This small picture. What's the physical origin? Who has idea? Okay, I just draw this picture. Draw this picture. Let me understand this figure. Why is it very important? It's a photonic crystal. This is photonic crystal. Okay, it's something. This is truncate here. So come truncation. Where you go here? This is truncation. Okay. Then, so I found this picture. So what's the physical meaning? From this picture, what's the information you get? Yeah, you can know the very important information. Xingao, you know this. What's the why they have a hotspot here? What's the meaning of that? Snow. Okay, from snow picture. This is very important. A lot of people cannot understand and figure out. This is standing wave. Okay, from incoming wave, reflected back, standing wave. So the distance between the two hotspots was this, half of the wavelength, LGO2. This is just waveguide wavelength over 2. Okay, so people use this also to the plasmonic. Okay, this nanowire, it has some reflection, to get this some standing wave. This is plasmonic standing wave. The plasmonic go here, return back, plasmonic standing wave. From this hotspot, we can know this is lambda GO2. Just plasmonic wavelengths. We can know the plasmonic wavelengths. Okay, it's very important. So people use this. They publish, I remember recently they use this graphene plasmonics. They do this something like this. This graphene, they count graphene. They have standing wave here. Standing wave something. Something like this. To know the plasmonic, graphene plasmonic wavelengths. They publish in Nature. Use just N-sum. Just measure, but they know the physics well. They explain this result. They know the wavelengths. Okay, so this is very important. So when you see a picture, oh, this is nice, but what's the physical origin? You don't know how to explain your result. Okay. It's just standing wave, very simple, a truncate. Okay, if this propagating wave is uniform, right? The amplitude is uniform, right? E minus jk is uniform. Standing wave has the this bright dark is standing wave. So this is very important to understand this small picture. Okay. So I have a 2-page. I can conclude this lecture. I have 2 pages. Why I move? Just yeah. So this is for N-sum. Okay. So everyone should know this principle. Okay. This feedback is, I think, is a very very tricky. Okay. You use this force and return back. So it's very pensive. Another microscopy is E-beam, similar to electron scanning electron microscopy. Okay. They just use electron gun to show the electron condense them with go to a pinhole and strike a sample. The sample scatter another second electron and detect. Okay, this is very simple. But the equipment is big, you can see. Very big. I'm not sure how much, but I think it's not or maybe it's also expensive. Okay. You can see this SEM. Okay, this is SEM image for this antenna the bow tie antenna in nanoscale. They do the SEM. This is another thing you can see. You can make this image quite well. Okay. So here, why the electron wavelength is very small, just 1A, right? 10 to the minus 10 nanometer. Okay, so they can break. So their resolution is much higher than the optical. Okay, so their resolution is good. This resolution is good. Okay, so this is a basic idea. Just strike electron, scatter electron, collect them from the stage. This is basic. Another is called a transmission electron microscope. Well, this is all the physics. It's very interesting. I copied figure. I found the figure in the internet. I spent a long time to find a lot of papers because there's no textbook, you know. All are collected by me. There's no textbook on this part. It's a transmission electron microscope. You can see if I shine the electron, go to a sample, what happens? First, there's an electron scatter. This is SEM, the back scatter electron. Another, they maybe emit the X-ray. Okay, they can do another. They can do another measurement. They do X-ray. Okay. The third type called RG electron. Remember RG, right? The electron from ground state to excite state to ground state to recombine with the hole. Addition energy will excite another electron go up and emit it. Okay, they call it RG electron. Okay. So they have a different name. If it goes to one electron here, a scatter one electron they call SEM, or scatter X-ray called EDS. Okay, I mean they call it RG. Or they have many different techniques to detect all the scatter particles. Maybe scatter RG electron, scatter secondary electron, scatter X-ray. They can detect them. Okay. They also can transmit it directly. Okay. There's an electron on scatter. They can transmission directly. Okay. This is TEM, or called EELS. Okay. This is called TEM. TEM picture, in the dark picture, electron cannot transmit it. Okay. Because TEM is transmitting electron. They collect the transmitted electron. Okay. If this metal is dark, it cannot transmit it. But here, it can transmit it freely. Okay. So they form the picture. Okay. It just transmitted. So SEM just scatter. Just scatter. So TEM resolution is much better than SEM. TEM can go to 1 nanometer, or even maybe much higher resolution. A scatter is weaker, maybe 10 nanometer or something. Okay. So this is the basic idea. So you can say this is a sample. They condense the electron beam. They are transmitted and collect. Okay. So SEM not transmitted, just reflected. Okay. You can see this from here, they reflected. So this is a basic difference between, okay, this last page. Just compare SEM and TEM. Okay. For SEM scattering electron microscopy, the electron was scattered. Okay. First, they can emit almost all kind of samples, conducting, not conducting. Okay. But they need surface coating with metal. Sometimes they need surface coating some metals to scatter electron. Okay, they might coating themselves. Another, they has no requirement for the electron transfer sample. Okay, TEM must that sample should be very thin or transparent. The electron can go past. Why else you cannot imagine anything? So they can imagine all the directions, just rotational sample. Okay. This is SEM. The resolution is low, just few, not too low. Okay, it should be higher than optical microscopy, but the field is tens of nanometer. It's because the electrons scatter. Okay, but TEM you can see here resolution you can see very high, 0.2 nanometer, very high for TEM. They have transmitted electron. Okay, then they can imagine crystal lattice. Why? Because they're transmitted, right? They can know the crystal lattice. They're transmitted. Know the crystal lattice. Okay. Also know the defect. Where's the defect in your sample? Because it's a transmission. Not a scattering. Scattering only surface, right? The only surface typically. No. If you transmit it, you can know the defect. Okay. This is called TEM. And no metallic coating needed. Okay. So it's very good. We also can do some other techniques. Okay. But there's a disadvantage. It's an electron transparent sample. Maybe the thickness or their conductivity. Okay, it should be controlled to make this. This is SEM and TEM. So finally, as a summary, so optical microscopy, initially people use some dark field use some phase contrast to enhance the resolution, but it's not good. Then people do small, near field scanning microscopy. They collect evanescent wave, and use FM feedback to control the distance between the tip and the sample, to enhance the resolution, But the SEM and TM, they use electron to strike your sample. The SEM just collect the scatter electron, TM just collect the transmission electron. Their resolution is much higher than optical part. So this is all the microscopy idea. On the next lecture, I'll talk about surface characterization. Because next lecture is the last lecture. I'll talk about its exam. Also. Well, thank you for attending my lecture.